Alright, so today I'm going to talk about return-oriented-exploitation on ARM. So first of all, who am I? So my name is Tokics. I'm a 15-year-old iOS/macOS developer, and I'm interested in ARM, mobile security, and software exploitation for about 2.5 years now. I'm also continuously working on some private older jailbreaks because my focus is on iOS and this jailbreaking process. But the main focus of this talk is to cover the basics of ARMv7 and ARMv8 registers, and also I'll show you a couple of differences between ARMv7 and ARMv8. Then cover the fundamentals of ROP exploit techniques, and in the end I'll show you a demo exploit. So let's start with ARMv7. So ARMv7, aka ARC32. ARMv7 has a fixed size of 32 bits, and there's a 16-bit mode available known as thumb mode. And on ARMv7 we have 15 general purpose registers, and these are labeled from R0 to R15. And from R0 to R12, From R0 to R12, these are the general ones. And from R13 to R15, those are the special types of registers. So R13 is a stack pointer, which is always points to the top of the stack. R14 is the link register, which is always holds the return address from, for example, when a function call is made. And R15 is the program counter, which is always holds the next instruction to be executed. Now ARMv8, on the other hand, is ARM64 or ARC64. We have a lot more registers, so like 30 general registers, and these are labeled from X0 to X29. And ARMv8 supports ARMv7 for backwards compatibility, but when this mode is enabled, the upper 30 bits are ignored, and the register names are actually changes a slight bit, so it changes from X to Ws. And so we have from X0 to X29 the general ones, and we have the same special registers like in ARMv7. So X30 is a link register, the stack pointer is its own register, so also referred as X31. And the program counter here is not directly modifiable. Means, for example, if you're writing in ARM assembly on ARMv7, you can just use R15, just as a program counter, but not on ARMv8. So ARMv8 supports expression levels as well, so from L0 to L3, and this is a physical separation of levels, so even to like rings, but that's actually beyond my talk now. So here's a couple of differences. So you can see first of all the register name, so like R0 and X0. Then instruction analytics, so like move the W on ARMv7. And the return instruction, so like on ARMv7 we branch to link register, and on ARMv8 we just write, which is basically the same thing, just with a different name. So here's differences when adding items to the stack. So on ARMv7 we have a push instruction which adds many specified registers to the top of the stack, and on ARMv8 it's actually subtract from the stack pointer, so it's actually manually grows the stack. Because in here, it's actually the stack is grows the exact opposite way what you think, so it's actually grows downwards. And then we have an instruction, so it actually stores a pair of register at a specified location. Now, what ROP stands for? So ROP stands for Return-Oriented Programming, and this is a modern exploit technique. The old-fashioned way was to actually use a shellcode to execute your malicious code, but nowadays actually you would chain gadgets to actually execute your malicious code. So here's what ROP gadgets are. So all ROP gadgets are found within the tag segment, so the code segment, and these ROP gadgets has to end with a return instruction, so a write instruction, because obviously that's how you can chain them together, and even hundreds of gadgets could chain together if the program allows you. So here's a quick diagram of how gadgets work. So you can see where we have the save return address, that's where we override the program counter, so, and we put our first gadget address there, which obviously going to point to the first gadget. And then once it's executed, it's going to jump back to or return back to the stack, and it's going on like with the gadget to address and so on. But as we all know, all bugs / vulnerabilities are different, and sometimes you only have one gadget's worth of execution. For example, when you dealing with a non-stack-based function pointer overflow, and there's a solution for that, and it's called stack pivoting. And by stack pivoting, you create a fake stack, and to be able to do that, you need to control the stack pointer. And to be able to control the stack pointer, you need a special type of gadget called pivot gadget. So here's an example of paper gadgets. So it's very simple. It's just actually moves the value of x1 to the stack pointer. So it's just basically overwrite it. And the last instruction just load x30 and return. So here's how kind of stack pivoting against stack pointer works. So we have the memory, and we can see that stack pointer now points to 0c. It means it's going to execute from there. So like 0x41. If we get an instruction to move down, then or pop, we can see it's now the stack pointer going to points to 10. And 0x41 doesn't need to be cleared because it just doesn't count as a stack anymore. Now, if you actually can control this stack pointer by our paper gadget, we can actually move there and we can control the whole stack. So we can just basically execute our rob chain. So here's a stack-based attack. So the very basics one are stack buffer overflows, and these types of overflows targets the stack. And the main goal is to override a function pointer with attacker control data. Alright, so this occurs when a program is run out of space, and you essentially start overwriting the function pointers. And the aim is to control the program counter. So here's actually a diagram of how overflow works. So you can see at the first picture is nothing allocated in the stack. The second one you can see a few is allocated, and the third picture you can see an overflow. And we can control this because we actually overwrote the program counter with A's. Now, I actually don't think this will work in modern systems because most modern systems have protection against these overflows. And modern systems have ASLR and DAP enabled as well. So yeah, what is ASLR? So, well, ASLR stands for Address Space Layer Minimization, and it's basically randomize all address in runtime. So you can see the first one, it was 0x16 FD0F790. And the second one was 16 FDE7790. So the two addresses are kind of different. So what's ASLR for? So ASLR for making the program counter control useless, because even if you can control the program counter, you just can't jump to anywhere because you just don't know where anything is. So it's also for preventing shellcode from being successful because it's just you don't know where anything is. Of course, there are a few ways to defeat ASLR. So I wrote down two. So the first one is a brute forcing, which is not very practical because it could take a lot of time. And the second one is an info leak, which I'll talk about a little bit. So the very basic info leak one is a format string vulnerability, and this is due to using printf in the wrong way. So you can see the attacker can enter basically anything, even %ps, to leak the data from the stack. So if you actually try to compile that program, the compiler will show us some warnings. So it will tell the format string is not a string literal, potentially insecure, and underlines the format string, which is in the wrong way. So you should actually use format specifier and then put the format string. So now testing this up is our binary. We see what we entered. So we entered high, and here's what the program printed out for us. So it's basically simply high. Now, all format specifiers start with a percentage. So what happens if you actually enter percentage high? So here's what we entered, and here's what the program printed out for us, some read output, because it's treated the percentage h as a format specifier. So percentage p purpose to print a pointer value, and if you actually enter a lot of percentage p's, you can see that the program printing out for us some stack pointers. So yeah, and usually one pointer from the stack is enough to defeat the whole ASLR by finding the function in this number and compare the leaked address, what we actually leaked, and then compare to the static address in the number, and the difference will be the ASLR side. Now, anytime you want to jump to an address from now on, what you want to do is basically get the address where you want to jump to and add the ASLR slide to it. So yeah, here's some heap-based techniques. So on the heap, you have basically dynamic allocation, and you can allocate by malloc and specify the size, and you can delocate by free and specify the pointer. So the first technique is actually Heap-based, and Heap-based doesn't actually exploit any security issues, so it's just like can't really be fixed by an update of a program. And Heap-based attempts to put a certain sequence of bytes at a predetermined location by allocating a large memory blocks on the heap. And you want to kind of think of a heap spray as you would spray wall with paint. So here's our diagram how it works. So we can see before the spray, basically nothing allocated on the heap, and after the spray, we can see a lot of knobs allocated, and then our shellcode. So we want to put consecutive knobs or no operations plus our shellcode, because the knob tells the program to move on to the next instruction, and this will happen until we actually reach our shellcode, and it will essentially execute it. So here's some heap Feng Shui. So heap Feng Shui, you actually carefully place objects in the memory, and repeating allocations, and we will have consecutive memory blocks, and after that the allocation can poke holes. So here's a general heap overview. So you can see the orange is in use and the gray is a hole. So you can see we actually don't know how the heap look like, so it's just like some of them are in use and some of them are actually holes. And now let's do the first step. So allocation is repeated often enough, so all holes will be closed, so let's just do that. And allocating a bit more, and we will have consecutive memory blocks. So now we actually kind of put our data to it, so we kind of know how the heap looks like now. And now the allocating can poke holes, so like we poked 2 holes. And essentially the next allocation will be into our hole. And so by this, a buffer overflow can be controlled, because if we actually control the data, or we can rewrite after it, the data before the new allocation, we can essentially control this buffer overflow. So user-free. User-free occurs when a program can need to use a pointer after it has been freed. And we often call this dangling pointers, and this could lead to arbitrary code execution. Now I took this source code from iOS 9.0's kernel extension, and what you want to care about is that if the device is not null, then what it will does is cause device terminate, and this calls OSRelease function and pass an argument as a device. So the OSRelease is the unsafe function, because if you actually check out how Apple actually defined it, we can see they actually didn't set an inst to null. So Apple should use OSRelease null. They actually quickly patched this by setting the device to null, so it's a bit of a shame. So yeah. Now here's the demo. So the target name is BSidesDemo, and the vulnerability is user-free, and the architecture which is available on is ARMv7 and ARMv8. So every time we want to exploit any binary application, we kind of always have a checklist. So first we want to find where the vulnerability could occur, then find the addresses for our rob chain, and in the end we want to carve the exploit and test it. So here's the first stage. So by running the program, we can see we have actually 6 options. We're interested in 5 because the 6 is just basically exit the program. So option number 1, we can basically allocate. So you can see the program tells us to enter some data to allocate. So maybe we want to actually check this function because a buffer overflow may could occur. Now I have access to the source code because I wrote this program, but you could get this by decoding from IDA or Hopper. So you can see we have by option number 1, we actually have a function called allocate object by user, and it passes an argument as input for alloc. So let's check this function. We can see at the scanf, it's actually kind of safe because I put %31s, which means this will only scan up to 31 bytes, and we need +1 for the null termination, and the buffer is 32 bytes, so it's perfectly. Now I again use the safer function, the store and copy, not the store copy, but we actually have an object stack data, so we actually want to check out that. So we can see it's actually defined by struct object and underscore object. And here's the struct, how it looks like. So this is basically a struct, and what you want to note down is that we have 2 function pointers sitting there. Alright, so now choosing option number 2, we can see it actually opens a file. So entering option number 2, we can see that the program is actually waiting for an input from the user. Now let's actually enter a path for a file to basically test this function, and we can see that it prints out the data was created with hello BSidesBUD, this is a test. And if you actually check what the file contains, it basically contains the same thing, but the program printed out for us. So let's check option number 2. So we can see it's actually called create data object. So let's check this function. So first of all, we can see that it's basically allocate 200 bytes on the heap. Now this part is just for scanning the path from the user and opening the file. And we have the fread. Now if you don't know what fread syntax, it says passing 4 arguments, and kind of be interested now in the first one. And the first one is a pointer, and it says pointer is a reference of an array or a structure where the data will be stored after reading. So it means it will store it to object data which is on the heap. So let's continue our journey. So you can see by option number 3, you can see that it actually allocates the device. And we get a message that the device was allocated. So by checking this function again, we can see it's basically what it does. It just allocates our 2 function pointers on the heap there. So yes, again, it's an struct. So now to actually free the data, we actually need to allocate first. If we don't do this, we might end up in a double free. So yeah, in theory, this option number 4 is only free the data what we entered by option number 1. But in reality, this basically what we can see here, there is a check. So if the object is not null, then it calls a function called terminate object, and it passes argument as object. And the terminate object just simply free a struct. So now we actually know where the vulnerability is, because it just I use it for free. Because the terminate object frees the object, but it doesn't set the null. So checking the heap layout before executing option number 3, you can see there's nothing on the heap. And continuing, we get the message that device was allocated. And we can see that our 2 function pointers are there. So just basically allocated our 2 function pointers. And if we actually call option number 4 or the terminate, we can see that a few addresses are masked, so like 3 1s and 3 10s. But most importantly, our 2 function pointers are there. So it means we can still somehow reference to these addresses and kind of overflow with opening a big file, bigger than 32 bits. Right. So yeah, we actually have this first part because we know where the vulnerability could occur. Now we want to find addresses. So this is the aim of the binary. So this is the secret code. Now, okay. Yeah, so the secret starts at 0x0000B950. So yeah, we can just jump there and we're done. But we can see if we actually jump to secret, we have a check here. Which a check variable is if a check variable is equals to 0, then it's going to print out for us that we are inside secret and terminating, and basically terminates. So checking out, we can see we have the check variable and it's set to 0. So yeah. Now checking this variable in the disassembler, we can see it's in the data section, which is good for us because it means we can actually write to it, because if this would be in the text segment, we just couldn't write it because the text segment is executable but not writable. But this data segment is not executable but writable. Now I actually placed directly to be in the data section anyways. So this means that we actually have to write a rope chain to modify the check value and then jump to secret with holding check the correct value. And you once again note that it also means that we actually have to execute more than 1 gadget. So here's what we know so far. So first we need to find the setup gadget to set up our registers. Then we need to find a correct write gadget to write the correct values to the correct address. Then we want to trigger the UAF block and then execute our rope chain. So here's the first part. So we want to find the setup and the write gadget. So I actually placed these gadgets into the binary because just to be easier to find it, and yeah. So we can see it's actually pops R0 and R1, R2 and program counter, but this means that we can control R0 and R1. So we basically have the setup gadget. Now here's the write gadget. So what we can see here is it stores a value found inside R0 to a memory location pointed by R1. Now this is perfect for us because, as I said earlier, we actually can control R0 and R1 values. So we have both of them are set up here. So now remember, we are actually working on the heap, and we have 1 gadget worth of execution. So we need a solution, and that is stack pivoting. So now we need to find a pivot gadget. So I actually placed this inside my binary. So you can see it just basically moves the value inside found inside R2 to the stack pointer. So it just basically overwrites the value. So now we have all the gadgets set up. So we can see that this is the secret code again. This is the code when if it will check equals to 0, it's going to jump here and it will exit. Now you're probably wondering why not jump just here and skip the check. Well, that would be too easy, and I wanted to demo how full wrap chain works. So yeah, now we have the judges. Now we need to craft the exploit. So here's how the exploit looks like. So we have basically the storage bytes, which will essentially fill up the heap, and this will overwrite our first function pointer. And yeah, so here we go again with the filled up heap. And this is where we override the first function pointer, and this is actually points to our pivot gadget. So after executing the pivot gadget, it will actually jump here, and this will the setup gadget. So this is the setup gadget address, and now we will load 111 into R0, and we will load the address of the check into R1. So now here's some junk characters, and here's the address of the write gadget. Again, here's some junk characters, and here's the address of the secret. So after executing this exploit, we can basically have full control over the program. So yeah, now all the checks are done, and here's the test. Yeah, so just running the binary. It doesn't really matter what we enter there. We allocate the device, and I just called option number 5 to just show you that it just basically prints out that first check was done and second check was done. And yeah, so this is the correct order. And yeah, I specify the path for exploit file. Now calling option number 5, you can see that pond, and here's a shell, and just execute the uname-a command. So yeah, the exploit is complete, and here's some useful links. So if you want to learn more about ARM exploitation, so the top one is especially a good one, and the last one is my GitHub repo where you can download this challenge from, and you can try out yourself. So yeah, this is my Twitter handle. If you want to follow any of my work, or if you have any questions later, you can DM me. But if you guys have any questions now, feel free to ask, and I will try to answer best I could. Thanks.